Good morning, everyone. My name is Prateek. I'm an engineer in the M3 team. If any IP lawyers ask, M3 has nothing to do with the car. I'm going to be talking to you guys about metrics at Uber, a few things we've learned building the system, some common patterns that we think are kind of cool, and then our open source metrics platform. I'm also a pacer, so I apologize in advance if that gives you a headache, and I'll leave about 5 minutes for questions at the end if you have any. If you haven't heard of Uber, we're a small technology company. We help match riders and drivers and so on. We love ourselves some microservices. True story, last night I was researching how accurate that number is. I was off by 1,000. We have 3,900 or something right now. We have a central observability platform. So there's a org that's responsible for metrics, logging, tracing, et cetera. Today we'll focus predominantly on the metrics. If you guys are interested in the tracing talk, I recommend checking out Yuri's presentation from last year. He gave a really great presentation about the sort of evolution of Jaeger and why he created it. Metrics are used for all manner of things at Uber. We use them, for example, for capacity planning, right? Like we figure out like load averages and figure out how many more servers we need based on that number. We use them for loading, so application metrics like your tail latencies over the course of like the last 10 minutes or whatever have spiked. You probably need to like look at something because like someone can't get a ride or something like that. We track business metrics. So, for example, the number of UberX rides currently happening in Portland. There's a dashboard somewhere that has that visualized. There's probably a load of it too, and plenty more. Right? People do interesting things and you don't really hear about it. So one really cool example of this was a couple of months ago. We were reading an RFC. Someone on my team found this. Uber is like a geo-sharded business, right? Like a lot of our stuff, as you'd imagine, depends on locality. You need to know like a driver's in this particular location and a rider's somewhere close by. So we have a lot of like geo-sharded services. One of these geo-sharded services was load balancing using M3. So they had this feedback loop that took metrics from the system, put it into their load balancer to figure out where to move stuff around, which in and of itself is cool. It was in production for about 6 months before we heard about it. And it's just like, okay, I mean, cool, I guess, but it was still like a nice realization that people do interesting things and you don't expect them to. This is what it looks like from the perspective of a developer to use the system. We have instrumentation libraries in pretty much every popular language at Uber. This is an example in Go. We have this like top-level construct called a scope. You can create metrics from it, and there's no restrictions on the names and so on. So here we're just creating a metric for a timer. We're timing the amount of time it takes to process a particular request. We're calling it latency. Very imaginative. And then further, we're tracking like response code to see, you want to break down the number of requests based on the response code that you got back from them. Nothing fancy, right? On the query side, this came up, I think, in Ian's talk. We have a query language. I won't go too much into it, but it's like a tag-based query language. It looks kind of similar to Bash. You can pipe things, and it feels really great. This is what it looks like to create one. It's a conceited example where I created a service called Monitorama, and just a drop down of like all the particular names for metrics that the service had. As you can see, like errors show up, latency, the one we just looked at, shows up as well. And we autocomplete just so that you can find what metrics are there. But this kind of helps when you know what you're looking for. But you can also like autocomplete when you don't know what's around, right? So you saw that top-level construct called a scope. It can already be tagged. So if you don't know what other tags are there, like this helps sort of identify that. But all in all, discoverability in this system is a problem. Imagine if this is for one service that you wrote, you kind of can find what you're looking for. But we have 3,900 of them, and like each team is probably responsible for 5 to 10 at least. I can't keep that amount of like context in my head. So people name things differently, different services do things differently, and all in all, discoverability becomes a problem at that scale. Furthermore, I think like a lot of people have discussed this and think it's a good idea. Like usually you care about measuring behavior and like monitoring behavior based on how your system is behaving relative to the experience the client gets. And for that, you want like these top-level like golden signals, if you will. Depending on who you ask, you get different answers for what these golden signals are. The SRE book points out those four. Brendan Gregg suggests the use method. Someone else suggests the red method. I really want to call out Baron Schwartz's work. I think he gives like a little bit of pedantry, but he's very formal about using terms the correct way. And I really appreciated the way he sort of structured his presentation. I'm not going to repeat it, but I do recommend checking out the video. All of this just to say that there are these golden signals that you kind of want to look at typically when you're looking at a service to understand what's going on. And then you can dig into specific parts. Because of that, we allow users to create dynamic dashboards. And this is just a tool where a user enters a service name, and we automatically generate a dashboard for them each time. Here's an example of one. And this is, again, generated completely on the fly, where every time you hit this URL, it generates this dashboard, and the user doesn't specify anything. So based on the metrics the user's service emits, these panels are pulled in. You can tell, right, like at the top, it's running in Mesos, so it just pulled in the Mesos panel. Similarly, there's like M3 usage. You can see it uses Cassandra. You can see it uses Redis, et cetera. And all of these things aren't specified at the user level. Like the user doesn't tell us that this is happening. They just use these libraries, and it automatically works. I'll dig into one particular row. It's called Motley. Motley is our software networking RPC stack. If you expand into that row, you'll see that it pops up all the error distributions, the success distribution, the latency, all of that, like all of those golden signals, if you will, per endpoint, per destination, et cetera. And you get it for free, right? Like a user doesn't have to tell us that these are the things they want. You automatically generate this for them. It helps a lot when a person doesn't have context about a service to sort of understand the top-level metrics. Further, you can also do this like across service boundaries, right? So if you know that A service talks to service B, you can pull in all the related dashboards. So every single callee relationship, you can figure out who's in what state. Like, has there been any alerts upstream? Has there been any alerts downstream? And it helps a lot in contextualizing what's going on in services. How does it work? Consider just any particular service, nice rectangle to represent that. It's made up of more smaller rectangles. The top level is sort of user code where you might have your RPC handlers, et cetera. And then these other blue boxes representing libraries that other teams, like storage teams or like software networking has written, sorry. Excuse me. Excuse me. And what's really great about this is a user doesn't have to do anything beyond just use these libraries to allow us to create these dashboards. So for example, they just provide us that service name and we can generate it. And the way that works is each of these service libraries, they tell us like there's a particular template, and at query time, we just query for that service, look at all the metrics that are there, and if any metric matches a pattern that we know this template satisfies, we can just pull in that row, and lo and behold, it works. It's really great. It works pretty well for us. Auto alerting. So we just talked about generating these dashboards on the fly, right? And this came up. I'm going to shamelessly use this opportunity to continue the Monitorama inception trend. Jamie had this subtle point in one of his talks about managing alerts, right? Where you specify a particular alert, and over time, it atrophies. Ian had the same point about migration systems between APIs and YAML. It's a problem, right? Like if people specify an alert, over time, that alert is going to change. Can we do the same thing that we did for dashboards for alerts? The way we handle this is we allow users to not have to specify these, and we generate alerts for them. So akin to we have Grafana dashboards for when you really want to dig into a particular subsystem or something, and we have these dynamic dashboards. The same way users can configure manual alerts, but they can also get these automated alerts. And we can do these based on RPC endpoints because we already have them. We can use those golden signals we were talking about to automatically generate them. We do a bunch of stuff like this with anomaly detection. It helps a lot. I recommend trying it out. But the first thing that comes to my mind when someone told me this was like, is this just going to cause an alert storm? Is it just auto-generating these alerts without telling a user? Or even if you told the user, like, what happens when stuff starts to blow up? And it does, right? Like, this is not something, if you auto-generate an alert, it's probably going to go off at some point. To handle that, we allow users to group alerts. So there's a rule specification where you can say, anything with this tag, only alert me for a single combination of it. Or any combination of tags, alert me only once. That helps a lot. We can also specify dependent alerts. So imagine a situation where you have a couple of different consumers running on the same host in a Mesos cluster. When that host is getting hosed, like if it's having EDAC alerts or something like that, those service owners shouldn't be notified, right? They can do nothing to fix that host. So what we do is we allow users to say that they're dependent on a particular platform. It's automatically triggered, and when an alert goes off for their service, and we can see that there's an alert going off for that host as well, we don't notify the service owners. We just notify the Mesos platform owners, because they're the only ones who can really act on it. This helps reduce that noise a lot, and again, it works pretty well. And further, when you get one of these alerts, you can provide so much context with those dynamic dashboards. Like you can jump to the right place and give the sort of surrounding context for what's going on, what surrounding services are affected, and it helps a person unfamiliar with the landscape to sort of get a sense of what's going on really quickly. We talked a little bit about dashboards. We talked about alerts. And if you consider sort of the OODA loop, right, you can observe, you can orient, but you can also act on it. To that effect, we allow users to remediate alerts a little bit. So if you have an alert that's triggered around a deployment, where if a deployment happens and within like a few minutes of that, your RPC metrics fall over, we automatically can roll back that deployment for you. Similarly, we have a configuration system. Imagine feature flags at scale. Everyone uses these. If you have a feature flag that's changed and an alert goes off, if your metrics start falling off a cliff, we can automatically roll back that alert, or roll back that configuration change. Again, it's got a couple of outages for us. It works really great. But all of this isn't particularly new, right? Like, what's so hard about all of this? Like, most of this stuff has been talked about, has been done, and it's sort of table stakes, I think, in today's day and age. And I completely agree. I think it is. What's been so hard for us to do all of this has been the scale of it. And I'm going to share some numbers with you about how hard it is for us. Here's what it looks like for the number of ingest metrics coming into our system. These are unaggregated. It goes up to like 600. Funny story about that, when we submitted the CFP for this, we said 500 million metrics a second, and we were sure that was like the peak. I was making these slides a few weeks ago, and it's like, it hit 600. Good to know. It seems to work. These are the unaggregated metrics. We further aggregate them, and these are the sort of metrics we store in our backend. That comes down from 400 to 600 to about 20 million per second. It's about 6 billion unique identifiers. It's a lot. And then on the query side, we get about 2,200 queries a second. We have roughly 9,000 dashboards in use, about 150,000 unique alerts that are run every minute on the minute. And this sort of translates to a lot of traffic out as well. It's about 30 billion data points per second on average, and it spikes much higher, as you can tell. Again, a lot of network traffic out as well. The worst part about this is that's just the number today. It's constantly growing. Here are just like some top-level stats of like how much they've changed recently. The 500 to 600 is just like one data point, right? It's insane to see the sort of scale of it keep growing. And for the remainder of the talk, I want to talk to you about the backend we built to support scaling it to this point. So quick history about how M3 is the team name, how we got to the point we are. Before the team was formed, Uber was using Graphite. Very similar to George's talk yesterday about Slack's migration and all the problems they ran into with Graphite. Everyone runs into these. If you've heard of Whisper files, I am really, really sorry. There's no replication, it's not sharded, so if a single instance goes down, you have downtime. If you want to do maintenance, if you want to expand your cluster, you have downtime. You lose metrics. It's not a great experience from an operator's perspective. It's a terrible experience from a user's perspective. And we really didn't like it. It was not scaling either. So very quickly, we made a backend using Cassandra instead. And that worked fine for a while, but it has its own warts. So between 2015 to 2016, we saw about a 16x growth in our metrics. And at that scale, Cassandra just didn't work for us. And I'll give you some specifics about why, but it starts to get really, really expensive. We were at about 1,500 Cassandra nodes before we finally migrated off it, which is a lot. My manager, yeah, if you guys will manage 1,500 Cassandra nodes, I'm sorry again. My manager likes to joke we're a technology company, not a telemetry company, if you know the reference. And the reason it gets expensive is Cassandra, like with our write workload, you just need a lot of compaction. And we needed so much scratch space, so much spare CPU to keep up with these compactions that we actually had to turn down our replication to RF2, which was terrible, right? Like the whole reason to make the system was to have more replication, to have like better reliability. And the system didn't give us that. We couldn't use repairs conceivably. Like a repair on a single node in our cluster took like 4 hours, and some of these nodes, like some of these clusters were 80 nodes. So the retention for the entire cluster was sometimes 2 days, and the repairs would take 15 days, at which point, what's the point, right? So we had to turn off repairs. Again, a really terrible like failure mode because we had to have hinted handoffs on because of RF2, and we didn't get the reliability we wanted out of it. So we sort of looked around towards the middle of 2016, like what are our choices? Like what open source solution exists that will scale to these numbers, that will scale for our future needs? And there were no open source solutions that did it, at least. All the vendor sort of paid solutions weren't cost effective, so we did what everyone does, and we rolled our own. we call it M3DB, and I'll talk to you guys a little bit about it. Here's sort of the top-level design goals for it. It's a pretty text-dense slide, so I'm not going to read it. But I will point out that most of the choices here, or most of the goals, are stemming from our pain. Like, we don't want compactions because we were burnt by them. We don't want, we want replication because we were burnt by not having it. We want the ability to bootstrap off other pairs really quickly and not do hinted handoffs because we were burnt by doing the alternative. So a lot of operational experience and a lot of operational burnout sort of contributed to our design a lot. And you'll see that throughout the rest of this as well. Really quick aside, we did also use TSZ compression, so call out for Gorilla, the paper from Facebook. A lot of people use this. It's like table stakes again, I think, at this point. If you guys aren't familiar with it, I'll give you like a quick description of what this is. This is quite literally borrowed from their paper. Consider if you want to store 3 like timestamp value pairs, right? If you do it naively, like 8 bytes per timestamp, 8 bytes per value, 48 bytes, I think, total. But if you realize the variation in these bytes isn't that high, so like from here to here, you only have like a minute and a second, right? There's no value variation. And this basically just does, sort of encapsulates that with like you track the start and then you track the variation. It does that for the timestamp, and then it does something similar for the value. It works really well. You get a bunch of compression. We took that idea and we sort of expanded upon it. We call it the sort of next algorithm. We use M3TSZ. It's a little bit better for our workloads. We make a couple of different trade-offs for it. We allow like a little bit of, so I think past the 6th decimal point, or it's a configurable amount of decimal points, we drop any values. That buys us a bunch of compression, and then we further do some header encoding to like stream the number of bits. There'll be a blog post to follow if you're not following this, but if you're curious about the code, it's right there. As you can tell, it's like a nice improvement over TSZ, which is already a pretty massive improvement over like the naive 16 bytes, right? That's the impact of one of our clusters using TSZ instead of Cassandra. For reference, Cassandra was using LZ4 at the time. And again, we're running at RF2, 1.4 petabytes, so total of 2,800 terabytes. And then for M3DB, at RF3, it was still only 600 terabytes. So like a 5.5x or 4.5x, yeah, 4.5x saving there, but also significantly more reliable. I'll dig into the architecture a little bit so you can see how that works. Logical constructs, if you don't follow this, the only thing I want you to get from here is for an M3DB database, it can have multiple namespaces, which are sharded, replicated, and so on. A namespace has a single index, and a database has a single commit log. Everyone with me? Great. Imagine a write comes in, you have multiple namespaces in your database. We typically like chunk up our namespaces. A namespace is basically a table in Cassandra. It's a table for us in M3DB. It has retention, resolution, and so on. So we have multiple namespaces in a single cluster in some cases. So the 2-day indicates 2 days of retention, and 40 days is 40 days of retention. Imagine a write comes in. We write to, like an in-memory TSZ or an M3 TSZ encoder. This is basically like a streaming encoder akin to what we were talking about earlier, like that, the TSZ thing. And these are sort of mutable. Once we know that they're done, we sort of mark them sealed, compress them, and then write them out to disk. We call these file set files, akin to like database snapshot files, if you will. And for durability, we also write each write to a commit log. It's basically a write-ahead log. So if you lose some data, like, or rather if you have your database come up, you get a write, it's in memory, node goes down, you don't lose any writes because all your writes are persisted into your commit log. Basically what I said in the previous slide in text form. Here's what the layout looks like on disk. And again, you'll see some motivation from the compaction story here, where we write out temporally. So there's a single commit log, you can see that right there, based on time. Similarly, there's a namespace. These are the TSZ files, file set files. Again, per shard. And then there's a single namespace, or single index per namespace. So these guys contain the sort of reverse indexing information. They have FSTs, postings list, etc. These guys contain all the TSZ encoded structures, the M3 TSZ encoded structures, I should say. Basically what I said in the previous slide, except for one little point, if you look at the sort of structure here, right, these keep growing over time. So if I was to say that anything older than time X, I can just RF that, right? I don't have to rewrite data. I don't have to do a compaction. It saves us a bunch to do this. It's so much cheaper on the CPU, so much cheaper on the disk. We really like it. Pardon me. Commit log is uncompressed for data. We compress IDs a little bit just to save some space. It supports both asynchronous and synchronous mode. Again, pretty common in most databases. If you need the durability, you run in synchronous mode. If you need the performance, you run in asynchronous mode. Batch your writes up and periodically fsync them. That sort of explains a single node. Imagine like you have multiple ones of these, right? It's a sharded replicated system. So for that, we maintain a topology in etcd. It's a strongly consistent store. All our writes are done by fat clients, so they're aware of the topology. They do the sort of async batching, making sure you do the quorum and all that correctly. And they're threaded, so it's pretty performant. And again, we don't do any hinted handoff. So if you have 3 nodes up, great, you can actually try the write. If 2 of your 3 nodes are down, it doesn't matter if that 1 node responds success, we will not accept the write. Just again, coming from experience of like compaction suck when you write a lot. That's an arbitrary scale, as you can tell. I wasn't allowed to share actual numbers for obvious reasons. But when we migrated from Cassandra to M3DB, we saved a bunch. Like, they both scale horizontally. Slopes matter, though, right? Like, and further, like, read performance. Like, I was actually really surprised when I made these slides. Like, these slides are over a year old, but like this one in particular, like, that number really scared me because an order of magnitude here or there, not a big deal. Like, I buy it. 2 or 3, and I start to like look at it kind of sketchy. And I made sure those numbers are right, which really blew me away. And it, like we said, we got more reliable, significantly cheaper, and it just performs better for us. What does production look like today for us? This is our stack per region. So we have agents running on hosts and remotely in other cases that people push metrics to. These guys can scrape metrics as well. They funnel all their metrics to an aggregation tier. This aggregation tier is another custom thing that I'll talk about. It has some really great properties. But this is the thing that takes like the 500 million, 600 million writes a second, and we didn't even recognize it. Scales like a, yeah. And then it has a bunch of different backends. We write to multiple M3DB clusters based on retention, resolution, and then we use ES with a whole lot of caches on both sides for performance, for obvious reasons again. And that's per region, so every region has some version of the stack running. And I mentioned this was OSS, right, like open sourced. Why are we doing that? I think it's an important question. Like Matt had this really great lightning talk, I don't know if everyone saw it yesterday, about like the motivation and all of that. And I really want to sort of stress on this point that like M3DB wouldn't exist without a lot of the work that already was done before us, right? The TSZ encoding, like we definitely built on top of that. We're standing on the shoulders of giants, and we want to pay that forward. We want to contribute back to the community, and we think that there isn't a solution that works quite as well. And if it can help people not have to reinvent the wheel, it'll be great. It's one of the primary motivations we're doing this. So if you want to try that, we'd be happy to have you. With that in mind, we're announcing, I sound like a person on the second floor, a sort of integration with Prom as a remote read long-term storage endpoint. M3DB here indicating that it has all of these things built into it. That's a sidecar that runs alongside Prom, and that's the node. You can run etcd embedded inside it. Has a bunch of nice properties. And there's docs if you guys are interested. One caveat, we run this currently in our smaller deployments, so like 5 to 20 nodes and so on. All the big like the 500 million metrics a second, all that, those clusters run with ES with all those caches. And that's predominantly because there's a bunch of features that the index still needs to add before we could support those workloads. We have the write performance pretty far up there right now. The read performance needs a little bit more work as well. So when we figure those out over the course of the next few months, this will probably become our default mode for even our larger deployments. But something to keep in mind. Where can you find it? It's on GitHub, like all our dev, like we literally build the binary, like I will occasionally build the binary from there and like test on a test cluster. So that's very much the code that we use. It's Apache v2, like a super permissive license. Like fork it, do whatever you want with it. We're happy to have you as part of the community. We'd love to work with you. We'd be happy to take contributions that you think would be meaningful. There are docs up there. There's a forum to reach us if you guys are curious. And I want to give you like a quick sense of like what is coming on up in the next few months, the next year, if you will. On the M3DB side, we need to like document some of the stuff better, and we want to like have a bigger release. So we look for a blog pretty soon. We're gonna add the ability to sort of backfill data. So right now, we only allow a configurable amount of forward and backward look ahead. So within that period, we'll allow any writes to come in, but outside of that, we won't. We want to change that, add the support for any backfilled bulk loading of data. Similarly, all the index stuff that I talked about, get the read performance up there, support multiple clusters instead of just a single cluster, add support for graphite in M3 Coordinator, which is our sidecar. We already have graphite metrics stored in M3DB. We can already index them, but we don't have the end-to-end server set up so that it's super easy to just hit an endpoint and it works. So we wanted to add all of that. And that's just on the M3DB side. On the aggregator side, and this is the thing that I showed you in the middle, it's already there. That's the code for it. It's just not in a state that's easy to use, so we want to make it easy to use. It has a bunch of nice properties that I think help people. If you guys are familiar with StatSite, think StatSite, but way better. It's sharded, it's replicated, it scales. It allows you to configure dynamic rules per identifier, per metric ID. You can say, on this tag, I want to roll up to X amount of time for these functions and so on. It's super powerful. And that's just the aggregation side. We want to open source our query language. We want to expose the query engine itself, and that's, again, something we're working on actively. And again, there's plenty more. The rest of our stack, there's no uber secret sauce there. Most of it can be open sourced, and we're working towards that. I had the privilege of standing here telling you about all this, but it's definitely the work of a lot of people. I'd like to thank all of these people for it, and if you wouldn't mind joining me for a round of applause for them. Okay. Thank you. With that, I'd like to thank you guys for being a great audience and being an absolutely spectacular conference. I'm happy to answer any questions you have about any part of my talk. Yeah?
What exactly is the readback and what's in ES?
Great. So the question was, what exactly is the read path and what is in ES? So for a production deployment, the query service either hits the cache or goes to ES. So we resolve our query into all the identifiers. And then from the identifiers, we figure out what retention resolution you have. That's all kept in ES. And then we hit the different retention resolution namespaces or clusters in M3DB to get the raw time series data. Does that make sense? Perfect. Go for it. I beg your pardon? Yeah. Cheers. Yeah. So the question is this stack regional or global and so on? This is per region. So we have one out in the west, we have one in the east, and in a few other places. We either get both the metrics piped into the things for those cases, where we run the aggregation tier in each data center, and if you need aggregated across data centers or regions, you'll pipe the metrics across those regions. So the aggregation tier will get both of them. Does that make sense? Cheers. Yeah?
So that's basically on a metric by metric basis, you decide whether you want to aggregate across data centers, or how would you decide which metrics need to be aggregated across?
It's not a metric by metric basis right now. It's based on higher groupings. So services can sort of opt into it. You can have, so I mentioned earlier that these guys can also scrape. So there are occasional cloud zones we scrape from, and we just pipe to an aggregation tier as well. So there's a little bit of configuration in YAML files in a couple of other places where you can specify that just get routed to this other location. These collectors can have multiple sort of endpoints that they target, so they can target a remote and a local aggregator. That takes care of it. Anyone else? Great. Well, thank you so much. Thank you, man.